Okay, so here we will talk about the charge isolated conductor. So it says if an excess charge is placed on an isolated conductor, that amount of charge will move entirely to the surface of the conductor. None of the excess charge will be found within the body of the conductor. Okay, so this is a property you might need to slightly remember this fact. Okay, so this is different from the isolator. For the isolator, it can has a fixed charge distribution, but for the conductor, suppose this is a conductor, then if we assume that there are some charges, no matter positive charge or negative charge, on this conductor, then all the charge will go to the surface. All the charge will go to the surface, and also E to be 0 inside the conductor. Because if there is some E field inside the conductor, and if there are some charges inside the conductor, then there will be a force acting on this charge, and then it will move until all of the charge are moving to the surface. Then, and there is no E field inside the conductor, then there will be no force, and then all the charges will be relatively stationary at the surface. Okay, so here it says the sine wave of a tiny portion of a large isolated conductor. Large means infinitely large. Infinitely large. Although you cannot draw infinitely large, but this large actually means infinitely large isolated conductor with excess positive charge on its surface, a closed cylindrical Gaussian surface embedded perpendicularly in the conductor. So here, this one is the Gaussian surface we define for this case. Half of the cylinder is outside, half of the cylinder is inside the. So this part is actually inside the conductor. Inside the conductor, it is not a very thin one. It's a thick one. So this is still the conductor, and half of the cylinder is inside the conductor, half of it is outside, and the axis of this cylinder is perpendicular to the surface. Of course, we still assume this the surface of this conductor is flat. It's flat, so we can define the axis of this cylinder is perpendicular to the surface. Okay, so here we try to use the Gauss law for this Gaussian surface, and for the top face, is one, which is actually this side. Yeah, you can imagine DA is pointing to the right side in this figure. Also, the E field also point to the right side, so that E and A are pointing to the same direction. So for the Gaussian law, for the Gauss law, it is E dot dA times epsilon naught to be Q enclosed. So for the Q enclosed, which is actually this part. Only on this part we have the charges, and the charges is like sigma. Sigma is the surface charge density. Surface charge density, as we define in the previous chapter. The surface charge density multiplied by the area of this circle is the Q enclosed of this cylinder. Okay, so this is Q enclosed sigma A, and on the left side for this cylinder, we have the top face, the bottom face, and also the side. For the side, you can simply imagine dA is perpendicular to the side, which is also perpendicular to the E field. So E dot dA will be 0. E dot dA will be 0 for the side. And for the bottom, as I mentioned, inside the conductor, the E field should be 0. So for the bottom face, E dot dA should also be 0. So the only term, so it includes the top, the bottom, and the side. So we know the bottom should be 0, the side should be 0. For the top, it is E times A. E times A, it is the E is uniform. So it is like E times the area. So we have E times A here. So altogether we have epsilon naught EA equals sigma A. So finally, we can cancel A. So how large is the cylinder is not relevant to the answer. So the answer is E equals sigma over epsilon naught. Sigma is a constant because it is a uniform charge density. We assume it to be uniform over the whole conductor plate. And epsilon naught is also a constant, if you still remember. So in chapter 22, we actually have derived an equation like this. If we have an infinitely large plate, which is a thin, and a thin and infinitely large plate, it will generate the E field as this term, sigma over 2 epsilon naught. Counting this side, for the upper part, E is it is this one. For the lower part, the E point to the bottom. Yeah. So it generate the E field for the whole space. But here we assume that this conductor is infinitely large and infinitely thick. So it only generates the E field on the right side. So we get a factor of 2 here. We get a factor of 2 here. We get a factor of 2 here. Because for this case, this is the plate. It generates E to be sigma over 2 epsilon naught. Generate E to be sigma over 2 epsilon naught. But here we have a large, of course, very large, and it generates the E field as E to be sigma over epsilon naught. So it's just like adding these two together, all of them pointing to the right side, something like that. But actually, for this one, we derive it from scratch using the definition of E field, and then we try to separate the plate into many small parts, and then we try to find the E field regarding to every part, and we add them together using integration. Here we use the Gauss law, having a similar results. So here we have a sample problem. It says the figure shows a cross-section of the spherical metal shell of inner radius R. So this is the inner radius. A point charge of -5 mu c is located at the distance capital R over 2, not actually at the center. From the center to the shell, if the shell is electrically neutral, what are the induced charge on its inner and outer surfaces? Are those charges uniformly distributed? What is the field pattern inside and outside the shell? Okay. So actually, this shell is electrically neutral, and here we have some negative charge inside the shell, and as much as this is a conductor. So we can imagine if we define a Gaussian surface, here in red color, as it is inside the conductor, and I mentioned that inside the conductor, the E field should be 0. So you can imagine E dot dA for this Gaussian surface is E dot dA integration should be 0 for this Gaussian surface. And in this case, this is the plus. This is the plus for this Gaussian surface. And according to the Gauss law, epsilon naught phi should be Q enclosed. So Q enclosed, this is 0, phi is 0. So Q enclosed for this Gaussian surface should also be 0. And here we have Q enclosed to be -5 mu. So for the inner surface, there should be induced charge of a +5 mu c on the inner surface, for the inner surface. So this is according to the Gauss law. So Q enclosed should be Q inner plus -5 mu c, and this is 0. This is 0. So we should have a Q inner to be +5 mu c. And the shell is electrically neutral. So the outer surface, Q inner plus Q outer should also be 0 because this is the shell is electrically neutral. So for two reasons. For this reason, according to the Gauss law, we got Q enclosed to be 0. For this one, the shell is electrically neutral. So Q outer, so this is Q inner, this is Q inner, this is Q outer, to be -5 mu c on the outer surface. And yeah, and actually for the outer charge, for the outer surface, the charge is uniformly distributed. But for the inner one, the charge is not. It's not. So suppose you put a test charge outside the shells somewhere here. You will feel that the E field generated by this whole object is like all the charge are just located at the center. Just located at the center. So it's just like this is a shield. This is a shield. We don't actually know the charge. Where is the charge inside the shell? But as much as we have this conductor shell outside, it's just like the whole thing has a charge all distribute at the center. This is not. This is maybe a bit difficult to understand, but it's not. I think it's also hard to get through that. If you couldn't understand that, yeah, just need some imagination. Because it's hard to tell how it distributes unless you have a computer software to simulate it out. Otherwise, it's hard to explain why it is so bad like that. Okay, so next we consider to apply the Gauss law for another case. Here we try to find the E field generated by a long wire or long plastic rod. Here it says a section of an infinitely long cylindrical plastic rod with a uniform charge density lambda. The charge distribution has and the field have a cylindrical symmetric. Because you can simply imagine for this long rod, when you pick this point, it should be generated. The E field generated by this point is something like, you can just find ds. Ds. This is positive charge, so it will generate E field pointing somewhere here, and then if you connect. So you can also find the symmetric part of ds prime, and then it will generate the E field pointing this side, and then they will eventually cancel the vertical component. Only the horizontal component remains. And as much as this rod is infinitely long, so yeah, every point you cut is the half point. Every point you cut is the half point. Because it's just like you integrating something from negative infinity to infinity. If you cut it from 0 to infinity and 0 to negative infinity, so it's still a infinitely long part. If you cut it at 1, 2, 3, it's still a indefinite integral. So sorry, not definite, a improper integral. Okay, so actually you can simply imagine that it has some sort of a cylindrical symmetry. No matter which point you cut, it is actually the half point. Okay, so here we define the Gaussian surface to be this cylinder. The height is h, which is not so important. Finally, you'll find that it is just cancelled. This is the radius. This is the radius, which is related to the distance of the point you concern to the rod. Okay, so this is the radius is r, the height is h. So now we try to use the Gauss law for this Gaussian surface. So this one is a cylinder, so it should include top, side, and bottom. Right, and bottom. So actually, we know that the E should be perpendicular to this axis. So for example, this point, the E field point to this side, for this point onto this side. It should be always perpendicular to this one dA and also this one dA. For the top one, for the top side, for the top dA pointing upward, it should be always perpendicular to the E field. So this one will contribute a 0. Likewise, for the bottom one, it always contribute a 0. So only the side will contribute the net flux. Only the side will contribute the net flux. And actually, it is symmetric. It's symmetric. So originally, we have an epsilon naught integration of a E dot dA equals Q enclosed. So Q enclosed is still Q enclosed here. Epsilon naught is epsilon naught. This is phi. This is phi. And as much as E is uniform, so we have a E times A. A is the area of the side. So this is a cylinder. If we try to consider the area, we try to cut it out. This cylinder, you try to cut it out like this, and then you try to expand it. So this the side becomes a rectangle. This is h. So the height of this rectangle is h, and then this circumference of the circle becomes this part, which is 2 pi r, So the area of this rectangle is 2 pi r times h, which is this one. So we got epsilon naught E 2 pi r h. And then for Q enclosed, the charge density is lambda. Lambda multiplied by the height h is the Q enclosed. So we have lambda h here. And in this case, we can make some cancellation. H and H can be cancelled. So that's it. So we can just move these terms over. We finally will get E to be lambda over 2 pi epsilon naught r, like this. This is the closed form expression for the infinitely long wire. Any questions? Okay, so we have another one. So here we have the planar symmetric to apply the Gauss law. So here we have a non-conducting plate, a portion of thin here. Here we have a thin infinite non-conducting plate with a uniform surface charge density sigma. Surface charge density sigma. Yeah. So here, this one we have a thin non-conducting. Here for conducting or non-conducting is not so important here. Yeah, but yeah, actually we have the surface charge density to be sigma, and then this is thin, and also we define the surface the Gaussian surface to be a cylinder. And the axis is perpendicular to this plate, to this non-conducting sheet. Yeah. So we also apply the Gauss law for this Gaussian surface. And as much as we know, the E field should be pointed to the right side for the right part, and the E field points to the left side for the left part. So the side wouldn't contribute any net flux at all. Only the left side and the right side contribute the net flux. So here, E dot dA will be EA plus EA. So one of it refer to the net flux regarding to the left face, and then this one regarding to the net flux to the right face. So we have EA plus EA equals Q enclosed. Q encloses here. The Q, the charge distributed here, which is sigma times the A. A is the cross-section area. Okay, so similarly, we can just cancel A, and finally we got, on the left side, we have 2 epsilon naught E. 2 epsilon naught E to be sigma. So finally, we get E to be sigma over 2 epsilon naught, like this. Which is actually the same as this one, which is actually the same as this one. So it actually tells you that you can actually find the same answer using 2 totally different methods. For this one, you don't really need to know what is Gaussian integral. The mathematics might be more difficult for this case, the mathematical background. But the calculation involved here we only have 1 line, 2 line, 3 line to the answer. So the calculation, the steps in between are easier. But of course, you need to know what is the surface integral. Here, we don't need for this one in chapter 22. You don't really need to know what is double integral, what is a Gaussian integral. We don't really need to know what is net flux. But the steps will be much more difficult. If you still remember, we need to separate this into many rings with different radius. We try to find the E field at this point regarding to different rings. We try to add them together using the integral. We still need to use the integration, but yeah, we don't really need to know what is this symbol. And yeah, so these are totally two different methods to find the same answer. Okay, here to apply for the conducting plate. So actually we can put two conducting plate. One is positive charge, another is the negative charge. Both have same amount of charge or same surface charge density, sigma 1, sigma 1. So this is positive, this is negative. So for figure A and figure B, if we assume that these two plates are placed far away, so we can just look at them independently. So for this one, we have a positive plate, and even though it's thin, we can imagine there are two faces. There are two faces, the left face and the right face. So it should generate the E field to be sigma 1 over 2 epsilon naught. Sigma 1 over 2 epsilon naught. For the left part, the E field point to the left side. For the right part, the E field point to the right side. For this one, this is a positive plate. And for this negative plate, the direction of the E field is opposite, but the magnitude remains the same. If we assume that the surface charge density to be the same, sigma 1. So here, for the left part, the E field point to the right side. For the right part, the E field point to the left side, just opposite to this case. Now we assume that we place these two plates close together. Then the positive charge and the negative charge will attract each other. So we assume that this is the positive plate, this is the negative plate. And as much as the charges, opposite charges will attract each other, so the positive charge will go to the right faces of this plate, and then the negative charge will go to the left faces of this plate. So in this case, you can imagine like this. You just add them together. For this part, for the very left part, we have sigma 1 to epsilon naught point to the left side, and then generate by this one, we have the E point to the right side with the same magnitude. So for this part, maybe use the highlight. For this part, which is like E plus minus is E minus. So it's just like this one minus this one, which is 0. And similarly for this part, on the right side for this one, we have E field point to the right side. And then for this one, the E field point to the left side with the same magnitude. So they cancel each other for the right region. So here we also have 0. We also have 0 for the right side, which is actually this one and this one. And for the middle part, you can imagine this is the right side to the positive plate and the left side to the negative plate. So they both generate E field onto the right side in this region. So they add together, which is like sigma 1 over 2 epsilon naught plus sigma 1 over 2 epsilon naught. So overall, the E field will be 2 sigma 1 over 2 epsilon naught, like this. Yeah, 2 sigma 1 over 2 epsilon naught, or Maybe the argument is not like that. The argument is not like that. Actually, it's like suppose all the positive are going to the right surface. So it is like this part also go to this side. So for this plate, it will already generate 2 times of this value. So it has E plus to be this one, all go to the right side. And for this one, this part will go to this side. So it's like 2 sigma 1 over 2 epsilon naught. All goes to the left side. So as much as they point to the same direction. So in between, we should have this E plus E minus, which will be also 2 sigma 1 over epsilon naught. And here we define this sigma to a new value, sigma, because this sigma is 2 times of sigma 1. So here, sigma is 2 sigma 1, because originally half of the charge are on the left side, half of the charge are on the right side. So they are sigma 1. And here, all the charge go to the right side. So sigma is 2 times of sigma 1 here with this expression. Okay. So still, for the parallel plate, so this is called the parallel plate. Parallel plate. Okay. There are only E field between these two plates. We'll assume the E field outside of these two plates are 0, and the E field are uniform. All points to the same direction between these two parallel plates, and the magnitude is sigma over epsilon naught, which is a constant. Sigma is a constant, epsilon naught is a constant. And actually, in chapter 25, we will use this, and we will see the capacitor again. So here is a sample problem. It says the portion of 2 large parallel non-conducting sheets, each with a fixed uniform charge on one side. The magnitude of the surface charge density, sigma plus, sigma minus. Find the electric field to the left, between, and to the right of the sheet. Okay, so here, E plus. Then we try to calculate E plus, which is a sigma plus over epsilon naught. It should be 2 epsilon naught. 2 epsilon naught. Because in this case, it will generate the E field on both left side and right side. On both sides. So it should be E plus over 2 epsilon naught. So it is 6.8 times 10 to the negative 6 over 2 times 8.85 times 10 to minus 12. So this one is 3.84 times 10 to the 5th Newton per Coulomb. So this is E plus generated by this plate on both this side and this side. And also this one also point to the right side, because when we try to consider E plus related to this one, so for this one to the left side, for these two parts onto the right side. So we have an E plus point to the right side here, E plus point to the right side here, and E plus point to the left side here. And for the E minus, it is a sigma negative over 2 epsilon naught. So we just plug in the value 4.3 times 10 to negative 6 over 2 times 8.85 times 10 to negative 12. So this is 2.43 times 10 to the 5th power Newton per Coulomb. Okay, so regarding to this one, the E field points to the right side because this is negative charge, and then point to the left side here. Okay, so we can see E minus, and to the right side for L and B, and then E minus point to the left side for R. Okay. So for the left region, we should have E plus minus E minus, because this one point to the left side, this one point to the right side. So part of them are cancelled. So we have a 1.41 times 10 to the 5th power Newton per Coulomb to the left side. And for the between the sheets EB, both of them are pointed to the right side. So we have E plus E minus. So we have 6.27 times 10 to the 5th power Newton per Coulomb. This one point to the right side. And for E right, we also have E plus minus E minus, because this one point to the right side, this one point to the left side. So the value is also 1.41 times 10 to the 5th power Newton per Coulomb. But for this case, it points to the right side. Okay. So far, any questions? Okay. Okay, so here we just recap the shell theorem in chapter 21. At that time, I just said that just mention the shell theorem, the two shell theorem, without mentioning the reason. But here, using the Gauss law, we can really explain why the shell theorem is correct. Actually, we can somehow prove it out. So at that time, there are two shell theorems. The first one is a shell of uniform charge attracts or repel a charged particle that is outside the shell, as if the shell's charge were concentrated at the center of the shell. So this one regarding to S2. So here you see this which specify the uniform charge density on a shell, on a conducting shell. So we have charge Q uniformly distributed here. Now, if we consider a point outside this shell, we can just assume a Gaussian surface with the same radius of this point, and then we draw a sphere there, and then this one is the Gaussian surface we would like to use, and applying the Gauss law to the surface S2, for which R is larger or than or equal to capital R. Capital R is the radius of the shell. We would find that E to be this one. If you don't remember, can just go through it quickly, like this. Q. Q enclosed is nothing but Q inside this S2. So this one, we have epsilon naught times E times dA is 4 pi r squared. So we just move all this term over. We will get E to be 1 over 4 pi epsilon naught r, and then times Q over r squared, like this. So which means that it's just like all the charges concentrate at the center. Charge are concentrated at the center. Yeah, nothing but that. And the second one is that if a charged particle is located inside a shell of uniform charge, there is no electrostatic force on the particle from the shell. So now we consider the Gaussian surface S1. Consider the S1 here. So here, small r is smaller than capital R. Small r is smaller than capital R for this case. Here we use this one to be the R for S1. Okay, so applying the Gauss law, there is no charges enclosed by this Gaussian surface S1. So we should immediately get that E dot dA to be 0. And as I mentioned, the condition uniform distributed is very important, because if the charge outside are not uniform distributed, we cannot assume that all the points on the Gaussian surface to be equal. Maybe if you consider a Gaussian surface like this, and then there is only a charge here, then for sure this point has a non-zero E field at this point. But when you consider E dot dA for this Gaussian surface, it should be 0. But the E dot dA is not uniform over the surface. So part of it is positive, part of it is negative, and they perfectly cancel each other. But here, as much as we have the uniform condition, so we can also imagine that if we have a uniform charge shell outside, then for this Gaussian surface, the E field, the flux is uniform. So as much as this one is 0 and it is uniform, so we will expect that all the E field on this Gaussian surface to be 0. So we get this one with the uniform charge. So this is the second statement for the shell theorem. And here we try to derive the E field for another case. Here, rather than a conducting shell, we have a non-conducting sphere. And we also assume that there is a uniform volume charge density for this sphere. And when we consider the point outside the sphere, the E field is nothing but usual. Just like all the charge are concentrated at the center. So we get K times Q over R squared when R is larger than or equal to capital R. However, if we consider the point inside this non-conducting sphere, it is not 0. It's not 0. And actually, we should consider the volume charge density rho to be this one. Q is the total charge amount. Q is the total charge amount. 4 over 3 pi R cubed is the volume of the sphere. I think you should You should have learned this in high school. So 4 pi r cubed over 3 is the volume of the sphere. So this is the total charge and the total volume. And if we consider a Gaussian surface has a smaller radius than this sphere, then it should enclose Q enclosed here, and then we have 4 pi r cubed over 3. This capital R refers to the radius of this sphere, and then this small r refers to the radius of the Gaussian surface. So they should equal to each other because the charge density is uniform. This is the charge density for the whole sphere. This is the charge density for the inside part. They should equal to each other. So we can just find the relationship between Q and Q enclosed. So actually 4 over 3 and 4 over 3 can cancel. Pi and pi can be cancelled. So we get Q enclosed to be R cubed. We move this over. So we have R cubed over capital R cubed times Q to be Q enclosed. And then applying Gauss law for this Gaussian surface, on the left side, we also get epsilon naught E 4 pi r squared. And on the right side, Q enclosed, which is nothing but this term. Let's put it here. So part of the R can be cancelled. R squared and R cubed becomes R. And then nothing else. So we have 4 pi epsilon naught, 4 pi epsilon naught to be here. And then we get R over R cubed, R over R cubed. And then also we get the Q here. So finally, we get this expression, K times Q, R over R, capital R cubed. The dimension is still the same. We still have some charges over a distance square. So this is distance cubed, this is distance. So when we cancel the dimension, it's just like distance squared. But actually, inside this uniform distributed sphere, the E field is increased proportionally to the radius. So this one is proportional to R. This one is inversely proportional to R squared. When we consider the outer part is inversely proportional to R squared. When we consider the inner part, it is proportional to the radius. So if you would like to draw it out, this is the radius of the sphere. For the inner part, it increased linearly. And yeah, so this is proportional to R. This part inversely proportional to R squared, like this.